Friends, in this video we shall try to understand what isotopes are and how their discovery changed the definition of atomic weight. In the year 1808, John Dalton proposed that atoms of a particular element are all identical to one another. That means all oxygen atoms are identical to one another, all chlorine atoms are identical to one another, all sodium atoms are identical to one another, and so on. That means all the atoms of a particular element in the entire universe have the same mass and size. In the year 1896, Henry Becquerel accidentally discovered that atoms of certain elements are spontaneously emitting some invisible particles. What do we mean by the word spontaneous? That is, without prompting, without we asking for it, or on its own. And this phenomenon was named as radioactivity, and substances that exhibit this phenomenon are known as radioactive substances. Now, some radioactive substances emit a kind of particle known as alpha particle, and some radioactive substances emit a different kind of particle known as beta particle. For example, radium emits an alpha particle. After emitting an alpha particle, radium transforms or changes into an entirely different element called radon. So the interesting thing here is a radioactive atom, after emitting alpha or beta particle, it changes into an entirely different element with different chemical properties. By this time, they already started the classification of elements based on their chemical properties. That is, grouping of elements that have similar chemical properties. For this, they arranged elements in the increasing order of their atomic weights in a chart called periodic classification table. Now let us say this is the position of a particular radioactive element A in the periodic table. This element is in this particular position because of its chemical properties. Now let us say atoms of A emit alpha particles. After emitting alpha particles, they transform into atoms of an entirely different element, and let us call that element B. Now if you look for the position of B in the periodic table, it will be two places to the left of A. This is where you will find B in the periodic table if this is the position of A, and this is not only true for A, it is true for every radioactive element that emits alpha particles. So when a radioactive element emits alpha particles, it changes into a new element whose position is two places to the left of it in the periodic table. Now let us say this element B is also radioactive, but let us say atoms of B emit beta particles and not alpha particles. After emitting beta particles, atoms of B transform into atoms of an entirely different element, say C. And based on its chemical properties, this is where you will find C in the periodic table, that is one position to the right of B. Again, assume C is radioactive and atoms of C emit beta particles and transform into atoms of yet another element, say D. Again, based on its chemical properties, this is where you will find it in the periodic table, one position to the right of C. But alpha and beta particles carry mass. When alpha and beta particles are emitted, some mass is getting kicked out of the atoms. So that means atoms of D are lighter than atoms of A. That is, they have different masses. Yet they have identical chemical properties and they are found in the same exact location. So Frederick Soddy, who was studying radioactive substances, thought that A and D are two entirely different elements with different atomic weights but identical chemical properties. That is why he called them isotopes. Iso means same, topos means location. Same location, where? In the periodic table. Then Soddy took a mixture of A and D and tried to separate them by using chemical reactions or chemical methods. And he found that it was impossible to separate A and D by using chemical methods. I am not saying it is difficult. It is impossible to separate A and D by using chemical methods because they have identical chemical properties. Though Soddy initially thought that A and D are two different elements with identical chemical properties, that is, isotopes are two different elements with identical chemical properties, he soon understood that they are in fact one and the same element. So isotopes are atoms of the same element with different masses. They are not two different elements. So for the first time, Soddy understood that atoms of an element need not be identical. They may not have the same mass and size. That means John Dalton was wrong. Dalton proposed that atoms of an element are identical and they must all have the same mass and size. But Soddy found that atoms of an element need not have the same mass. Today we discovered that there are many elements that have more than one naturally occurring isotopes. If you take oxygen, it is a mixture of three naturally occurring isotopes called O16, O17 and O18. Similarly, chlorine is a mixture of two naturally occurring isotopes, chlorine 35 and chlorine 37. Now, the relative abundance of different naturally occurring isotopes of an element is called its isotopic composition. For example, if you take a sample of oxygen consisting of a large number of oxygen atoms or oxygen molecules, it contains all these three naturally occurring isotopes of oxygen in these proportions. That is, for every 100 oxygen atoms in that sample, 99.738 of them are of this isotope, 0.0367 are of this isotope, 0.187 are of this isotope. And the interesting thing with isotopic composition is it is pretty much the same everywhere in the world. You take a sample of oxygen from Hyderabad, or you take a sample from Mumbai, or from Los Angeles, or from any other place. The isotopic composition of oxygen is pretty much the same. There may be a slight variation, but we can ignore that for our purpose. And another interesting thing is, the isotopic composition of an element is same irrespective of the form in which it is present. See, in air, oxygen is present in elemental form in the form of oxygen molecules, and it is also present in the form of carbon dioxide. But whether it is in elemental form or in the form of carbon dioxide, the isotopic composition of oxygen is same. Now, the discovery of isotopes has created some confusion with the definition of atomic weight. By definition, atomic weight of an element is the ratio between mass of one atom of the element and 1/12 of the mass of one atom of C12 isotope. That is our latest standard or reference for atomic weights. But when you say mass of one atom of the element, mass of which atom of that element? Earlier we thought that all atoms of an element are identical, so it did not matter because they all must have the same mass. But after the discovery of isotopes, we understand that all atoms of an element need not be identical, so they may not have the same mass. If you take the case of oxygen, it has 3 different types of oxygen atoms in nature with 3 different masses. So when you say mass of one atom of oxygen, mass of which atom of oxygen? So there is some confusion with this definition after the discovery of isotopes, right? Now, before we continue, let us understand some vocabulary. After the discovery of isotopes, what do we mean by an element? For example, oxygen. By oxygen, I mean oxygen as it is present in nature. That is, a mixture of all the naturally occurring isotopes of oxygen present in these proportions. So by oxygen, I am not talking about any particular isotope of oxygen. But if I want to talk about a particular isotope of oxygen, I would clearly convey that. I would say O16 or oxygen 16 to refer to the most abundant isotope of oxygen. To refer to this isotope of oxygen, I would say oxygen 18 and so on. Now let us take the example of chlorine. Chlorine has 2 naturally occurring isotopes known as chlorine 35 and chlorine 37. And their relative abundances are 75% and 25% approximately. That is, out of every 100 chlorine atoms, 75 are of this isotope, 25 are of this isotope. So this is the approximate isotopic composition of chlorine. Now what is the atomic weight of chlorine 35? From this, you can clearly understand that I am talking about a particular isotope of chlorine called chlorine 35. It will be mass of one atom of chlorine 35 over 1/12 of the mass of a C12 atom. That is our standard or reference. Similarly, the atomic weight of chlorine 37 would be mass of one atom of Cl37 over again our reference, that is 1/12 of the mass of one C12 atom. And we experimentally found out that the atomic weight of this isotope of chlorine is approximately 35 and that of this isotope of chlorine is approximately 37. Actually, that is why they are called chlorine 35 and chlorine 37. Here, because we are specifically talking about a particular isotope, instead of calling it atomic weight, we can also call it as isotopic weight. So atomic weight of Cl35 and isotopic weight of Cl35 mean the same. So isotopic weight is the atomic weight of a particular isotope of an element. So this is some new vocabulary that we need to understand. Now, what is the atomic weight of chlorine? See, here I am not talking about any particular isotope of chlorine. I am talking about the element chlorine as it is present in nature. That is a mixture of both the isotopes of chlorine with this isotopic composition. But because chlorine is composed of two different isotopes with two different atomic weights, there is no single atomic weight for chlorine. So every time you deal with chlorine, you have to deal with two different isotopes. Maybe there is another element with 5 naturally occurring isotopes. So every time you deal with that element, you have to deal with 5 different atomic weights, and that would be annoying. So now the question is it possible to come up with a single atomic weight for each element, though it may be composed of different isotopes? I think there is a way. Remember, the chemical properties do not depend on atomic weights. See, chlorine 35 and 37 have different atomic weights, yet they have identical chemical properties. You cannot separate them by using chemical reactions. So as far as chemical reactions are concerned, we can imagine that all the chlorine atoms in the entire world are identical, though they are not. If all the chlorine atoms are identical, then what would be the mass of such an imaginary chlorine atom? Simple. This is the approximate isotopic composition of chlorine. Out of 100 chlorine atoms, there are 75 of this type and 25 of this type approximately. And these are the approximate atomic weights of these two isotopes of chlorine. Now imagine that you combined these 100 chlorine atoms into a big lump of mass. Then what will be the mass of this lump? There are 75 of them with a mass of 35 units each, and 25 of them with a mass of 37 units each. So the total mass of this lump would be 75 times 35 plus 25 times 37. Then you are dividing that lump into 100 equal identical atoms. So when you divide it with 100, you will get a value of 35.5. And this is what we call weighted average. And this value is what is called the average atomic weight of chlorine. So average atomic weight of chlorine is the weighted average of atomic weights of different isotopes of that element, taking into account their relative abundances. Generally, we omit this word average and simply call it atomic weight of an element. So average atomic weight of an element and atomic weight of an element are one and the same. It is the weighted average of different isotopic weights of an element, taking into account their relative abundances. And the average atomic weight is the atomic weight of the imaginary atom if all the atoms of an element are identical. So when we say the atomic weight of chlorine is 35.5, we mean this imaginary average chlorine atom is 35.5 times heavier than the reference we chose. Therefore, the atomic weight of an element can be defined as mass of one average atom of the element over 1/12 of the mass of one atom of C12 isotope. That is our standard. And in general, if A1, A2, A3, etc. are the isotopic weights of different isotopes of an element, and P1, comma, P2, comma, P3, etc. are their percentage abundances respectively, then the formula for the atomic weight of the element will be A1 times P1 plus A2 times P2 plus A3 times P3 and so on over P1 plus P2 plus P3 and so on. And because these are percentage abundances, their sum must be equal to 100. Finally, what is the atomic weight of chlorine? See, here I am saying chlorine in general, and I am not referring to any particular isotope of chlorine. That means I am referring to this imaginary average chlorine atom. A chlorine atom that we would have if all the chlorine atoms in the entire world are identical. And as we calculated here, the atomic weight of chlorine would be approximately 35.5, or the average atomic weight of chlorine. Now, what is the atomic mass of chlorine? Again, here I am referring to the element chlorine in general, not any particular isotope. So, to get the atomic mass, you always have to multiply the atomic weight with 1U. So, atomic mass of chlorine is 35.5 times 1U, that is 35.5U. Now, what is the atomic weight of chlorine 35? Here you can clearly understand that we are talking about a particular isotope of chlorine, and we know that its atomic weight is approximately 35. And we can call the atomic weight of a particular isotope isotopic weight as well. So, atomic weight of chlorine 35 and isotopic weight of chlorine 35 mean the same. And same here. Then what is the atomic mass of chlorine 35? Same thing. You take the atomic weight and multiply it with 1U. So, it will be 35U in this case and 37U in this case. Though there are many elements that have more than one naturally occurring isotopes, there are some elements that have only one naturally occurring isotope each. Such elements are known as monoisotopic elements. Examples are gold, sodium, aluminum, phosphorus, cobalt, fluorine, etc. Each of these elements has only one naturally occurring isotope.